All right, today we are going to dive deep into the invisible engine that's powering so much of modern AI, the vector database. This is a technology that has totally changed how machines see the world, so let's get right into it.
So here's our game plan. We're going to start with the fundamental shift from keywords to meaning. Then we'll talk about the language of AI itself, vectors. From there, we'll dive into the wild quest for similarity. Check out the indexing magic that makes it all possible, see how it scales in the real world, and finally, wrap up with why this is now the absolute backbone of modern AI.
To really understand vector databases, you have to start with the why. What problem was so huge that it needed a brand new type of database? Well, the answer is all about a massive shift in how we find information. For decades, search was basically a game of match the word. You'd type fastest car, and the system would just go hunting for documents that had those exact two words. But that whole approach has a huge, glaring weakness. It doesn't get what you mean. See, modern AI is different. It searches by semantic meaning. It actually tries to figure out the concept or the intent behind what you're asking. And that one shift, that move from just matching words to understanding meaning, is what broke traditional databases and created the need for this whole new thing.
So if AI isn't using keywords anymore, what is it using? It's using a mathematical idea that has pretty much become the universal language for artificial intelligence, the vector.
At its core, a vector is really just a long list of numbers, but it's a special list. It's created by a specific kind of AI, called an embedding model, that takes any piece of data and translates its meaning into this numerical form. It's kind of like creating a unique mathematical fingerprint for an idea. And what's amazing is that almost anything can be turned into a vector, a sentence, a picture, a whole document, even a clip of audio. The embedding model captures the essence of that thing and plots it as a single point in this gigantic, multi-dimensional space. And here's the magic. Things with similar meanings land close to each other in that space. Okay, so this is where things get really tricky. In this new world of meaning, there's no such thing as an exact match. There's only closer or further away. And trying to find the closest neighbors in a space with hundreds or even thousands of dimensions, that is a massive computational headache. This headache actually has a famous name, the curse of dimensionality. Think about it. In our normal 3D world, we get what close means. But imagine a space with 1,000 dimensions. As you add more and more dimensions, the space gets so incredibly vast that weirdly, everything is far away from everything else. Our whole intuition about distance just completely falls apart. So if you just tried to brute force it, checking your search against every single vector in a database of billions, well, you'd be waiting forever. So how do you solve this? How do you find the closest matches efficiently when you're dealing with this kind of massive scale? Well, you cheat, but you do it in a really smart way. The solution is called Approximate Nearest Neighbor Search, or ANN. And the core idea is a trade-off. You give up the guarantee of finding the absolute 100% perfect match in exchange for the ability to find a good enough match almost instantly. Every single real-world vector database relies on this compromise. Without it, they just wouldn't work. The secret sauce that makes this high-speed, approximate search possible is called indexing. This is the brain of the vector database. It's the set of clever algorithms that organize all those vectors in a way that makes finding neighbors incredibly fast. This table really shows you the fundamental trade-offs. You could use a flat index, which is just brute force. Sure, it's perfectly accurate, but the speed is just terrible. A more balanced approach is IVF, which groups similar vectors into clusters. But for pure, raw performance, most modern systems use HNSW, which is a graph-based method. It is crazy fast and super accurate, but the trade-off is that it does eat up more memory. HNSW. If there's one acronym you need to know in this space, it's that one. It stands for Hierarchical Navigable Small World, and it really is the state-of-the-art for high-performance vector search. It's what's under the hood of most major vector databases today, and it works by building this really cool multi-layered graph. So how does it actually work? Well, imagine a highway system with multiple levels. You enter at the very top layer, which has these long-distance express lanes that get you to the right general area super quickly. Then, once you're in the right neighborhood, you descend down to the lower, denser layers. Think of these as the local city streets, to navigate precisely and find your exact destination. It's this hierarchical approach that makes it so incredibly fast. But, in a real production system that's handling
billions of vectors, just one algorithm is rarely going to be enough. So let's look at how these different techniques are actually combined to build a complete, scalable system that can handle the real world. This is where things get really creative. Production systems use what are called composite indexes, where they might combine a clustering method like IVF with a compression technique like product quantization to save a ton of memory. They also use metadata filtering, so you might say only search vectors from the last 24 hours to shrink the search space before you even do the expensive vector part. And maybe most importantly, they often use hybrid search, where they blend old-school keyword search with vector search to get the best of both worlds.
And all of this brings us to the big picture. Why do all these technical details matter so much right now? Because this isn't just another kind of database. This has become a truly foundational piece of the entire modern AI stack.
Just think about retrieval augmented generation, or RAG, the technique that powers so many of the most advanced chatbots. The vector database is the retrieval engine. It's the thing that finds the relevant facts and context for the language model to use. And if that retrieval is bad, if it pulls back the wrong information, the AI will just confidently make things up. It'll hallucinate. The quality of your AI is directly, and I mean directly, tied to the quality of your vector search.
And this quote just nails it. It's so much better to stop thinking of these as databases for storing stuff and start thinking of them as powerful search engines for navigating geometry. They're this incredible fusion of advanced math, complex algorithms, and huge distributed systems.
And that's really why this matters so much. As AI gets woven into everything we do, understanding how to navigate information by its meaning, well, that's not just a niche technical skill anymore. It's becoming fundamental infrastructure literacy. This technology is a new set of building blocks for whatever comes next. The only real question is, what are we going to build with it?